Hello everyone. Today you're going to be looking at molecular polarity, and in order to do so the following things will be really helpful to have with you. A periodic table that has electronegativities, which you can find in your homework packet. If you flip through and you find the page right before the covalent bonding worksheet, you'll see that there's electronegativities in that periodic table. You'll need your notes, and that might be it. Alright, so in the past we have talked about bond polarity. Well, today is molecular polarity. You'll see that it is something different, but it's based on the same idea. So if you recall, there was bond polarity, and that was when you have bonds which have a larger range of electronegativities between the atoms. So if we looked at anything pretty much bonded with fluorine, which is over here, fluorine has a very high electronegativity, and if we look at another element far away from it, they can have very low electronegativities. Well, the largest difference will give you ionic bonds, but then there's also the difference between polar covalent and nonpolar covalent. So if you remember, there was a breakdown where if you have a difference in electronegativities, which is if it is between 0 and 0.3. Do you remember what kind of bond that is? It is nonpolar. That means that electrons are distributed evenly between the two elements. So they're shared evenly. If it's between 0.3 and 1.7, do you remember what that's called? Well, now you're starting to get a bigger gap in electronegativity, so this is called polar covalent. Okay, and this is when electrons are shared unevenly. Okay, and then anything greater than that, once you have electronegativity difference greater than that, you have ionic bonds, which means that an electron is completely transferred from the metal to the nonmetal. Okay, so those are the three types of bonds and in terms of their polarity. Okay, so nonpolar electrons are shared equally. The polar bonds, electrons are shared unequally, and the electrons tend to hang around that more electronegative atom. Okay, so more electron density is towards the electronegative atom. Okay, so there's this thing called dipole moments that we can use to show really that direction of the polar bond. So here's a molecule, HCl. Which one of those is more electronegative, hydrogen or chlorine? Well, we go over to our periodic table and I show you chlorine. You can see chlorine's electronegativity up here is 3.16. Hydrogen's electronegativity is 2.20. So chlorine is significantly more electronegative than hydrogen is. And that means that electron density is going to hang more around chlorine. So what we're going to do is we're going to use these things called dipole moments, which are really just an arrow that shows the direction of the more electronegative atom within a bond itself. So if I'm going to draw that, I'm going to draw the arrow from the hydrogen end to the chlorine end, and I'm going to put this little hash bond or this little hash mark on that positive end side. So remember from covalent bonding we talked about the delta plus and the delta minus. That just means partial positive charge on the hydrogen, partial negative charge on the chlorine, because chlorine it's kind of hogging that electronegativity a little bit. Okay, so that's within a bond, right? And for HCl, hydrochloric acid, it actually is the whole molecule itself, because there's only one bond in that molecule. So what we're going to look at today is how we can take that polarity term and apply it to whole molecules as opposed to just bonds. So what we're going to find is that there are sometimes molecules which have polar bonds but are nonpolar molecules. That's a very bad way of drawing the molecule out. You can also have nonpolar bonds and polar molecules. You can have, let's see, polar bonds and polar molecules. And you can have nonpolar bonds and nonpolar molecules. Do you see how this works? So just because the molecule is nonpolar altogether doesn't mean it doesn't have nonpolar bonds. Okay, so we have polar bonds, polar molecules, we have polar bonds, nonpolar molecules, nonpolar bonds, nonpolar molecules, and nonpolar bonds, polar molecules. Okay, so there's 4 different classifications of these molecules. Alright, so how do we know if an entire molecule is polar? Well, like I just said, whole molecules can have that polarity designation, but it might end up having polar bonds with, and the entire thing is nonpolar. This is the thing it depends on right here. We have to look at where are there dipole moments within the molecule and how do they add up. And we need to look at molecular shape as well. So this sum of dipole moments, I'll show you how you can add them up. And then we'll look at some molecules and their shapes and see how you can predict whether those dipoles will add up just by looking at the structure. Okay, so first off, let's look at nonpolar molecules. Nonpolar molecules are when you have a very symmetric shape. The dipole moments cancel out when that molecule is very symmetric, and there's no net dipole moment overall. Okay, so if all the dipole moments that are drawn in cancel each other out, then there is no net dipole. So let's look up this molecule. We have BF3, boron trifluoride. So boron and fluorine, we're going to have to look up first the electronegativity differences for the 2 atoms involved in all of the bonds. So we have BF, BF, and BF for all 3 bonds. Well, if I switch over to my electronegativity periodic table, I see that boron's electronegativity is 2.04 and fluorine is 4. So boron is 2.04. No, I already forgot. Is that right? Yep. And fluorine is 4.0. So we know that it's actually more like ionic. But for this case, we're going to just show how this molecule draws out. So with boron in the center and fluorines all around it, the Lewis diagram looks something like this. And the shape of that molecule, you'll notice that it is 3 bonding domains. How many non-bonding? Hopefully you counted 0. 0 non-bonding. So if you have 3 bonding domains and 0 non-bonding, what shape is it? Remember from last set of notes, you should know that it's trigonal, planar. It's flat. It's a flat molecule. Okay. So if I look at these bonds, just in general, fluorine is the more electronegative element, so it's going to end up with a partial negative charge. Boron is the less electronegative, so it's going to have the partial positive. Well, when I draw in my dipole moment, I'm going to draw it from boron to fluorine and put the hash side on the boron side. But I need to draw that in for all of the bonds. Okay, So all of those dipoles are essentially pulling towards fluorine, okay, and all that electron density is kind of shoving towards those fluorines. Well, if you think about tug of war, when you have if you only had 3 atoms to deal with instead of 4, you would see that, depending on, suppose it was the fluorines on the ends as well, fluorines would each be pulling with the same amount, and so would anyone win? Well, no, because the electron density is being distributed evenly out to the fluorines. Now when we start getting more atoms like BF3, there's 3 atoms attached to the boron. So if we look at, some of you have taken physics, but if you've got a central spot, and you've got one going up, one out to the side, and one going out to this side, there's a way we can describe the different directions. There's x components to this dipole, and there's a y component. Okay? So in this up and down one, there's only one component. It's the y component on the x. If we are going to, let's draw in that was terrible. Let's try again. Here's our xy coordinate system. There's only a y component on this top dipole. But on the bottom, like the bottom two, there's a y component. Come on, little pen. There we go. And there's an x. There's a y, and there's an x. Okay? Because of the size of each of these, we can say that this x component is probably equal. So they cancel. Okay? So that cancels with this. Well, then you have this top one and these 2 bottom ones. These 2 are going to add together to counteract the upward component. And now this will cancel with this. Now that was one hot mess of a way to say all dipoles cancel in BF3. Okay? It's because of physics. So when we draw out our dipole moments, we drew them out so that they were pointing to the fluorines, and all of the x and y components canceled out. So there is no overall dipole moment on this molecule. Okay? So we call that nonpolar. The key thing here, it's symmetric. Very highly symmetric. Polar molecules, on the other hand, are asymmetric. Okay? So if we were to look at water, H2O, which one is more electronegative, hydrogen or oxygen? If you're not sure, jump over here. Hydrogen has electronegative 2.2, and oxygen is 3.4. So it's oxygen. Okay? So oxygen is more electronegative. And so when we draw in our dipole moments, who are they going to point towards? They're going to point towards oxygen. And both of them point towards oxygen. And since you have both bonds are OH bonds, they're both pointing, they're essentially the same length of dipole moment. Okay? So if we've got our molecule over here, we draw in our dipoles. Well, here's the thing. We get our XY coordinate system again, and we have those 2 lines. Do they cancel each other out? Well, their X components do. Those cancel. But what does their Y component do? It adds. So when you have both dipoles pointing in the same direction, at least in the y direction, they add together. they're in opposite directions, they cancel out. Well, that means because there is an overall, this is our overall dipole moment, that is on the molecule like that. Okay, so on this molecule, there's a net dipole of the part of the dipoles that don't cancel. That's the net, and it points up through that oxygen. Put that hash mark on the positive end. So on the water molecule, the positive end is where the majority of the hydrogens, we've got all that hydrogen density here. So electron density is hanging out towards the oxygen. It's also because of those two lone pairs that are hanging out on that oxygen. Okay? So here's the key thing to know. Polar molecules are either asymmetric in shape or they're asymmetric atoms. Well, what are the asymmetric shapes? You can look at trigonal, pyramidal. Spelled that wrong. Pyramidal. There we go. Trigonal pyramidal. That one is asymmetric in shape. Bent is asymmetric. Any others? Just for, I mentioned this shape in the last set of notes. Seesaw and T-shaped are also asymmetric. Any others? I can't think of any others. The rest of them are very symmetric. So these are asymmetric. And therefore, they will be polar. Okay? The symmetric shapes would be linear, trigonoplanar, tetrahedral, square planar, trigonal bipyramidal, octahedral. These are all highly symmetric. Okay? And likely non-polar. Okay? When I talk about asymmetric atoms, what I mean is you don't have all the same atom attached around the central atom. Okay? So here's an example. CHCl3. Well, CHCl3 starts with a tetrahedral shape, right? Well, tetrahedral is right here on our list of being symmetric, and so likely nonpolar. But when you change the structure, so let's put a carbon in the center, we get one hydrogen, and we'll put in a chlorine. I'm going to clean this up. Okay, so now this molecule, this is chloroform. Chlorines are a lot bigger than hydrogen, so that's why it looks kind of funny. But this molecule, is this symmetric? It's got some degrees of symmetry. You can rotate it this way and have it be the same as you rotate it. But when you rotate it this way, you definitely notice that it's being rotated. It is not symmetric that way. So this molecule does have, if you look at it from this angle, you see that this far side by the, can't draw on the structure like I can with the other app. But over on by the chlorines are they have most of that electron density. So I want to show you something really quick. If I can remember how to do it. So if we look at this, shrink this down a little bit. Where it's the reddest, that's where that electron density is. Okay, so it's definitely asymmetric in terms of its electron density because it doesn't have the same atom attached around the central atom. That hydrogen end it has way less electron density. Okay, so in CHCl3, if we were to look at where the dipole moments are, chlorine is more electronegative than carbon, and so those dipole moments are going to point towards the chlorines. Carbon is more electronegative than hydrogen, so it's pointing down towards the carbon. If you think about the net dipole and whether these dipoles cancel out, well, around where the chlorines are, that electron density is pointing down. If we look at the molecule from this angle, you can see that they're evenly pointing outwards towards the chlorine. So those outward components do cancel out. It's just this up and down component does not. And since those two down components add together, the net dipole of this molecule is downward. Okay? So the things to look for our molecules. I'm going to go back to our slide. We have these. Okay. If the molecule has polar bonds and it's a polar molecule, it's most likely because it is asymmetric. Okay. If there are polar bonds and it's a non-polar molecule, that means it's probably symmetric. Non-polar bonds and polar molecule, again, it's asymmetric. Non-polar bonds, non-polar molecules, this means it's symmetric. So it all comes down to symmetry. Okay? Put onto your graphic organizer if you add this information here, that trigonal, pyramidal, and bent are your asymmetric shapes, then if you draw out your Lewis diagram, you identify that it's trigonal pyramidal, you're going to know that that molecule is most definitely a polar molecule. Okay? So I think that's the end of the notes. I wanted to show you a couple of examples. So first off, let's do pH 3. Okay? So if you flip over to your electronegativities of atoms, or just looking at your periodic tables, phosphorus is over here. Phosphorus has 5 valence electrons, and its electronegativity is 2.19. So P is 5. Electronegativity is 2.19. And hydrogen has 1 valence, and there's 3 of them. Its electronegativity is 2.2. 2.2. Yeah. Okay, so there's 8 valence electrons. Who's in the middle? Phosphorus. We put in our 3 hydrogens around it, and we've used up 6 electrons. So there's 2 left. Where do they go? Well, hydrogens do not want any more electrons, so we're going to place them on phosphorus. So that's our Lewis diagram. And remember, if we're trying to find the shape is based on the number of domains. So we have 3 bonding domains and this 1 non-bonding. Okay, so what shape is this? Well, hopefully you are using your chart and you see that when you have 3 bonding and 1 non-bonding, it is trigonal pyramidal. Okay. Based on the shape, it appears it's going to be a polar molecule, right? So it should be a polar molecule. if I draw that molecule out, I'm going to go to build, here, get a phosphorus, I'm going to put some hydrogens on it, I'm going to clean it up a bit, make it pretty. It is in fact trigonal pyramidal. Let's see if I can show that electron density. You can see, let's shrink it a little bit. Where's it the reddest? Over here on the phosphorus side. This is definitely a polar molecule because of the shape. So it's a polar molecule. But look at this. What kind of bond is that? 2.2 minus 2.19? That's well below 0.3. So this is definitely non-polar bonds. So this molecule has no dipoles in the bonds, but it is a polar molecule. Isn't that crazy? So non-polar bonds, polar molecule. It's possible. How about another one? What if we have carbon tetrachloride? Carbon is 4 electrons. Chlorines are 7 times 4 is 28. So 32 electrons. Carbon in the middle. Chlorine has an electronegativity of 3.16. Carbon is 2.55. 3.16 minus 2.55. It's definitely greater than 0.3. So this has polar bonds, for sure. We use 8 electrons in the bonding, so 32 minus 8, 24 hopefully. We place in those last 24 electrons. Okay, well, there's 4 bonding domains. 0 non-bonding. That means the shape is what? Hopefully you said tetrahedral. Okay. Well, let's flip back a few slides. Tetrahedral is highly symmetric and therefore nonpolar. So the molecule has polar bonds, but the molecule is itself nonpolar. Okay? Let's build it before the battery dies. Carbon in the middle. Chlorines around it. Clean it up. Looks pretty symmetric. I put in that electron density. Notice that it is equally red at every end. So it is very polar going towards those chlorine atoms in terms of the bond, but the molecule is so symmetric that all of those dipoles completely cancel out. Okay? And that, my friends, is polarity. If you need any extra help or have any further questions about bond polarity, make sure you send them on my way. Otherwise, there is a homework assignment in your homework packet. There's another video that I'm going to make to show you how to do hybridization, and then you'll be able to complete that entire last homework molecular geometry practice worksheet. All right, have fun!